This next series of videos is going to introduce you to the idea of goodness of fit hypothesis testing. As an example, we're going to look at a data set related to the one thing on all our minds at the time this video was made, which is the coronavirus. Now, there's been a lot of interesting math going on in terms of modeling the spread of this global pandemic, but one of the applications we're going to focus on here is in estimating the incubation period for the disease. I'm going to break this concept down a little bit more on the next slide, but for now, think of the incubation period as the amount of time between exposure and the onset of symptoms. So when an individual becomes symptomatic. So time between these is what we call the incubation period. And it's an important quantity to know, right? Because during this time, if you have the coronavirus, you're walking around and you don't know you have this disease, and so this is really a dangerous time for spreading it to others. Now, the two papers we're going to be drawing from in this study were, in this series of videos, was a study by Bakker et al. And a study by Lauer et al., both with that same goal of estimating the incubation period for this disease. The two graphs shown on this title slide are the CDF functions estimated by the authors of these respective studies. And they're fairly similar, as you can see. Now, just as an example of how to read one of these graphs, let's focus on the one on the left. Right, so let's take a time of 5 days just as an arbitrary value. So if we draw a line up to the CDF function and we look at the corresponding value on the y-axis, we can see that the probability that the incubation period is less than or equal to 5 is approximately, it looks like 0.35 maybe. Right, so that means about, according to these authors' estimation, about 35% of all coronavirus people infected with disease will start to show symptoms 5 days or fewer after infection. That's slightly different than the estimate obtained on the right, where 5 was much closer to the median of the disease, but overall the graphs are still somewhat consistent with one another in shape and values. So we're going to actually focus on the graph on the left in this study, the data set that was used to generate that graph. This was a study by Bakker et al. Now, what made this study kind of interesting is they looked at 88 of the first confirmed cases that took place outside of the Wuhan province in China. All of these cases were confirmed during the period of January 20th to January 28th. What I thought was interesting about this data set is included in there were 25 people that had been visitors to the Wuhan province for a fixed amount of time. And therefore, I think these 25 visitors are really a good sample to use in kind of honing in on what the incubation period of this disease is. Why? Well, let's look at the graph on the right. So these visitors had a predefined date of arrival in Wuhan, right? So this you could think of as an exposure start time for these individuals. And they also had a predetermined date of departure, so you could think of this as an exposure end. Excuse that random mark there, that stuff happens. So somewhere in between these two values, right, was the true exposure time. And what we're going to do is we're going to assume that that true exposure time was just the midpoint of this interval, right? Now, they also have a predetermined time where they started showing symptoms, or at least felt like they started showing symptoms, right? And so we're going to use this period of time here between when they were exposed and when their symptoms started to show. This is what we call the incubation period. And that's the quantity we're trying to estimate. Now, this is the actual histogram of incubation times for those 25 visitors to the Wuhan province. And so you can see that in this case, the bulk of them had incubation times of between 2 and 6 days, but there was one person who was as long as, I think it was actually 11 days was the upper bound here. So the 4 parts we're going to include in this video series. The first one, we're going to do a brief review of maximum likelihood estimation. And we're specifically going to look at 3 distributions here, the gamma, the y-bowl, and the log normal distribution. All 3 of which are kind of the most common classes to use in fitting right-skewed data like we saw in this slide right here. Right? If I was going to kind of draw a graph over the top of this, it would definitely have a long upper tail to it. The second video is going to introduce the chi-square goodness of fit test. The third video is going to show how to apply that goodness of fit test for continuous data. We'll also mention in this video a sort of more advanced version called the Kolmogorov-Smirnov test. And then finally, in the fourth video, we're going to come back and look at what do the professionals do, right? What did they actually do in these studies to hone in and get a better estimate on the incubation time for the disease? So I hope you join us for those ones as well.